So in this video we're going to talk about how we can convert a system where we have multiple forces and multiple couple moments to a system that has only a single force and a couple moment. The reason we're interested in finding in doing this conversion down to a smaller amount of systems is that typically engineers will design systems of rigid bodies that will be connected at joints, and then so examples of those would be like machines, frames, and trusses. So we want to know, as a designer, it's very important to know how the loads that are transmitted or applied to one member will be transmitted to another member. So if we can reduce the multiple loads that are applied to one member, we can determine what is the transmitted load at one of the joints. Okay, and then later on in your engineering career, you're going to take a mechanics and materials course, which is going to talk about how you can use these loads that you're going to show are transmitted to the different components of an engineering system to select the appropriate material for that application, and also the geometry of that rigid body so it won't fail. Okay, so there are two types of transmitted forces. So if you have a force that is parallel with a rigid body, typically what will happen here, all right, is that someone will apply if a force is applied to a rigid body like this, all right, in order to keep this rigid body in equilibrium, you'd have to have a joint, or if you thought of it as a person would have to hold this stick at another end. So what ends up happening is the person applies a force at the other end to keep the stick in equilibrium. But if we look at the person's hand, the force that the person's hand feels, or that is transmitted to the person's hand, is equivalent to that original applied force. Alright. So in a similar fashion, if you had a yardstick, but instead of applying that force parallel with the body, you applied a force perpendicular with it, and you tried to hold that stick with your hand. All right. What would end up happening, all right, is that in order to keep this stick in equilibrium, you'd have to apply a force going in the opposite direction. But from last videos, we talked about couple moments. So you can see we have two forces that are equal and opposite of one another. So in order to keep this in equilibrium, we also have to apply a couple moment to the stick to prevent it from rotating. Okay, so what ends up happening is your hand will feel the following loads. All right, it'll feel a downward applied force. All right, and it will also have a couple moment applied to it. Okay, so these are examples of Newton's third law, where we have equal and opposite forces at our joints. So this force here is equal and opposite as this force here, and then this couple moment and the force applied in the case of the force when it's applied perpendicular to the body is equal and opposite as the force and couple moment that are applied to the hand. Okay? All right. So we'll follow this procedure when we're trying to simplify a system of multiple forces and couple moments to down to a single force and couple moments. So we're going to start off with our rigid body, which I'll define. Alright, it can be any shape, right? And we can have a couple forces. Being applied to our rigid body, and we'll also have a couple moment being applied to our body. Alright, so the first thing we're going to do is we're going to select a point of interest. Okay, in this case we're going to use point O. Okay, alright, and then the second step we're going to do is we're going to determine we're going to take all of our forces and our moments and we're going to apply them at point O. Okay, so we're going to have force 2, force 1, our couple moment. Alright, and then we're going to have 2 additional moments due to force 1 and force 2. So we'll get let's see here, we'll get M2, and we'll get M1. Alright, where M1 is R1 cross F1, and M2 is equal to R2 cross F2. And so now we have everything at a single point. So the last step is we just need to sum all of our forces together and all of our moments together. So we're just going to use the following 2 equations. To do that, we're just going to say that the resultant force is equal to the sum of all of our forces. Alright, which in this case would be equal to force 1 plus force 2. Alright, and then our resultant moment about point O would be equal to the sum of all of our moments about point O plus the sum of any couple moments that were applied to our systems. In this case, it would be equal to moment 1 plus moment 2 plus our originally applied couple moment. Okay, so alright, so what this ends up looking like is at point O, we end up getting just a single resultant force and a single couple moment. And that, so please note that this is only true, or when you do the simplification, the value of your resultant force and the value of your, well, the value of your resultant force won't change, but the value of your resultant moment is only valid at point O. If you change the location of the point, your resultant moment will change.